There was no weak signal. No partial data. Nothing. More than 12 billion miles separated Earth from the spacecraft, and for nearly 2 weeks, one of humanity's most distant active missions appeared completely silent. The problem came from a simple mistake. A command sent to Voyager 2 caused its antenna to point about 2 degrees away from Earth. 2 degrees might sound insignificant, but across billions of miles, it was enough to break communication completely. Engineers at NASA's Jet Propulsion Laboratory knew they had very little room for error. Voyager 2 was already operating with an extremely limited power supply, and every command sent into deep space required patience. The spacecraft was about 18.5 light hours away. That meant a signal took roughly 18.5 hours just to reach Voyager 2. Then engineers had to wait another 18.5 hours to discover whether the spacecraft had responded. So they tried something remarkable. NASA used the powerful Deep Space Network antenna in Canberra, Australia, to send a command toward Voyager 2, essentially telling the spacecraft to reorient itself toward Earth. Then they waited. For more than a day, there was nothing. Finally, on August 4, 2023, the signal returned. Voyager 2 was alive. Data began flowing again, and after nearly 2 weeks of uncertainty, the mission was back in communication. But the recovery was only one part of the story. Voyager 2 was carrying something much more valuable than proof that the spacecraft had survived. It was continuing to collect information from a region of space that humanity has barely explored at all. To understand why that matters, we have to go back to 1977. Voyager 2 launched on August 20, 1977. Voyager 1 followed just 16 days later. The original mission was never supposed to last this long. The spacecraft were designed primarily to explore Jupiter and Saturn, with an expected mission duration of only a few years. Instead, they became 2 of the most productive robotic explorers ever built. Voyager 2 eventually visited all 4 outer planets: Jupiter, Saturn, Uranus, and Neptune. It revealed active volcanoes on Jupiter's moon Io, discovered previously unknown rings around Uranus and Neptune, and photographed Triton, where nitrogen geysers were erupting from the surface. Voyager 1 followed a different trajectory. After its encounters with Jupiter and Saturn, it was sent on a path that carried it rapidly out of the plane of the planets and toward interstellar space. That difference in direction is incredibly important. The 2 spacecraft are not following the same road through space. They are sampling different regions beyond the influence of the Sun. Voyager 1 crossed the Heliopause in 2012. Voyager 2 followed in 2018. The heliopause is not a physical wall. It is the region where the outward pressure of the solar wind becomes weaker than the surrounding interstellar environment. Beyond it, the spacecraft did not enter a perfect vacuum. They entered the interstellar medium. And this is where one of the strangest discoveries begins. Scientists analyzing Voyager 1's plasma wave instrument found a faint, persistent signal in the data. It was around 3 kHz. The signal was not a dramatic explosion. It was not a giant radio burst. It was more like a quiet background vibration that remained detectable over long periods. Scientists eventually realized that this faint emission could be used to study the density of the plasma surrounding Voyager. That changed the way researchers could monitor interstellar space. Previously, one of the best opportunities to measure the plasma density came when powerful solar eruptions traveled outward from the Sun and disturbed the material beyond the heliopause. Those events were useful, but they were occasional. The faint background plasma waves provided something different. A continuous way to monitor the environment. Imagine trying to understand the weather by waiting for a thunderstorm. A solar eruption would be the thunderstorm. The persistent plasma waves were more like the quiet background rain. They were always there. Scientists simply had to learn how to listen. And this discovery revealed something important. The space between stars is not completely empty. It contains charged particles, magnetic fields, waves, turbulence, and changes in density. Voyager's measurements have shown that the local interstellar environment has more structure than the simplest picture of empty space would suggest. Every measurement gives scientists another tiny piece of information about the region surrounding our solar system. And there is an unexpected connection between these measurements and some of the most distant explosions in the universe. Fast radio bursts. Fast radio bursts, or FRBs, are incredibly short flashes of radio energy. Some last only milliseconds. They can originate billions of light-years away, yet their signals reach Earth carrying information about everything they passed through along the way. One of the most important properties scientists measure is called dispersion. Radio waves traveling through plasma do not behave exactly as they would in a perfect vacuum. Different frequencies experience slightly different delays. The amount of that delay reveals information about the material between the source and Earth. An FRB may travel through the environment surrounding its source, through its host galaxy, across intergalactic space, through the Milky Way, and finally through the interstellar medium surrounding our own solar system. Voyager's measurements therefore provide a direct look at the final part of that journey. That does not mean the Voyager hum is responsible for fast radio bursts, and it does not mean Voyager is measuring the entire distance to those sources. Instead, the spacecraft are helping astronomers understand the local plasma environment that radio signals must pass through before reaching Earth. And that is valuable because even a small uncertainty in the local environment can affect larger astronomical measurements. The universe becomes even stranger when we move closer to home. Around Jupiter's moons, spacecraft have detected electromagnetic waves known as chorus emissions. Ganymede, Jupiter's largest moon, has a complex magnetic environment where energetic particles interact with plasma. Those interactions can generate electromagnetic waves. When scientists shift those frequencies into the range humans can hear, the result can sound almost like an eerie electronic whistle or a strange bird call. But it isn't ordinary sound traveling through space. It is electromagnetic data converted into audio so that our ears can experience something our senses cannot normally detect. The same general principle applies to many of the so-called sounds of space. They are often not sound waves moving through a vacuum. They are measurements of electromagnetic waves, plasma oscillations, or other signals translated into frequencies humans can hear. Mars provides another fascinating example. NASA's Perseverance rover carried microphones to the Martian surface, allowing scientists to record actual acoustic sounds on another planet. For the first time, humanity could hear the mechanical noises of a rover moving across the surface of Mars. The recordings revealed something very different from Earth. Because Mars has a much thinner atmosphere, sound behaves differently there. Some frequencies travel differently, and the environment produces an unusually quiet acoustic landscape. The result was a reminder that even something as familiar as sound can behave differently on another world. Put all these observations together, and a larger picture begins to emerge. Space is not simply a giant, featureless void. It is filled with plasma. It contains magnetic fields. Particles move through it. Waves propagate through it. Stars erupt. Planets interact with their environments. Neutron stars produce enormous bursts of radiation. And even the apparently empty space between stars has measurable structure. That is why Voyager's faint signal is so important. These spacecraft are now operating in an environment that no other human-made probe has explored in quite the same way. But Voyager 2's 2023 communication failure was a warning of how fragile this extraordinary mission has become. The spacecraft are more than 4 decades old. Their radioisotope thermoelectric generators are slowly losing power as the plutonium inside them decays. Engineers have had to make increasingly difficult decisions about which instruments can remain powered and which must be switched off. Every watt matters. Every instrument that continues operating represents another opportunity to learn something about interstellar space. Eventually, the spacecraft will no longer have enough power to operate their scientific instruments and transmit useful information back to Earth. That ending will not necessarily look like a dramatic failure. There may be no explosion, no final warning,